Good morning, everyone. Hope you're all well. Okay, so homework to the last question. You don't need to do it. I'll add it on assignment 3. The last question entirely, you don't need to do it. Apparently, I said in class that, guys, please, hey. Apparently, I said in class that you don't need to do the last part only. No, it's entirely optional. I mean, you're gonna have to do it eventually, like, okay? But yeah. Okay, so let G be a group. I hope to be able to return to you the homework by Friday, the graded homework one by Friday, I hope so. I think the questions are graded are, find an example where you have the composition is bijective, but none of them is bijective. And counting how many surjective functions you have. And what else will I grade? Yeah, I mean 2 more. I forgot what they are. But yes.
So the last question entirely is optional.
Is optional. I mean, you'll have to do it next week. Okay?
For the next one.
Yeah, for next homework. I'll just add it to next homework. Okay, so it's optional for Friday. Okay? Okay, so before guys, please, before I start, I mean, we have to show 2 things. I want to show 2 things. Then, the identity element, e.g., is unique. Okay? Now, how to show that? Suppose that e.g. prime and e.g. are 2 identities for circle. We need to show that e.g. is equal to e.g. prime. Now notice, what is e.g. prime? If E is the identity, then e.g. prime is E times 4. Agree or not? Do you agree with this? Since E is an identity, E is an identity. So when you apply the operation of E with something else, you get that something else. Yes or no? At the same time, e.g. prime is an identity. Right? So when you multiply E by e.g. prime, you get e.g. Okay? Great. Now I will show that inverses are unique. Now, can I drop the circle notation? May I just use, instead of writing this, may I just use this? Is it okay if I use this? Is it okay if I use this right now?
No, use the circle.
Okay.
Keep using the circle.
I will eventually have to drop it. I won't try to circle every time.
As long as you can.
We'll see. Okay, but are you comfortable if I remove the circle? Is that in general, or you prefer I keep the circle?
No circle. No circle.
Let's keep it for now. I mean, okay. I mean, we'll have to drop it. I won't try to circle every time. Okay? Great. We need to show that EG is equal to EG prime. Now, let G be in G, then, oops, there exists a unique H in G such that G circle H is equal to H circle G is equal to H. We call H the inverse of G, and we write H is equal to G first. Okay, let's prove this. So let H1 and H2 satisfy GH1 is H1G is equal to EG, and GH2 H2G is equal to EG. Then H1, what is H1 equal to? It's H1 times EG. Okay? Now what is EG? EG is, what I want to say is G times H2. Right? I just replace EG by G times H2. Then, what do I know about this law? It's associative. Now H1 times G is equal to EG. So it's EG times H2, which is equal to H2. So H1 is equal to H2. Okay? Is it clear? Any question? Okay? We good? Great. Awesome. Now I think I want to do something on the symmetric group, or maybe we can let's do something about symmetric group. This won't last a long time. I just want you to know some basic calculations. I think we're going to get back to this later, but just for the beginning, I just want you to get familiar a bit with the notation. Okay, so let X be a set. The set of bijections from X to X that I will call Sim-X, symmetries of X, Sim-X, is a group under the law of composition of functions. Okay? We've seen this last time. Now if X is 1, 2, up to n, Sim-X, we write it as Sn, and call the symmetric group on n letters. Okay? Now let's give a small example. For n is equal to 3. I need a bijection from this set to this set. Let me pick this bijection. 1 to 2, 2 to 3, and 3 to 1. 1, 2, 3, let's call it F. F is equal, so where does it send 1 to? 1 goes to 2. 2 goes to 3, and 3 goes to 1. This is clearly a bijection, right? So it's an element of S3. Now, how do I write this one more concisely, in a better way? There's a way of writing these. Okay, we agree that this is a bijection. F belongs to S3. Since F is a bijection from 1 to 3 to 1 to 3. Are we good or not? Yeah? Clear? Okay. Now, this notation is a bit long to write. Now there's a nice way of writing this. I'll write f as, so first pick a number. Let's start with 1, okay? I write 1. Where does 1 go to? 2. 1 goes to 2, so you write 2. Okay? Where does 2 go to? 3. You write 3. Where does 3 go to? It's back to 1. You close the bracket. Okay, is it clear? Let's do one more example. Let's do one more. We do one more example? Yeah? F, let's say 1, 2, 3, 4. 1, 2, 3, 4. I'll switch 1 and 3. And switch 2 and 4. Okay, F is in S4, right? It's a bijection from 1, 2, 3, 4 to 1, 2, 3, 4. Okay? How do I write this? F, what do you want to start with? What's the best way to start? 1. Where does 1 go to? 1 goes to 3. Now where does 3 go to? 1. So you close the cycle. You close the bracket. Now, are we done? What do you have? 2. Where does 2 go to? 4. And where does 4 go to? Okay? Clear? We do one more? Let's do one more. F 1, 2, 3, 4. 1, 2, 3, 4. 1, 3, 3, 4. 4, 1. And 2, 2. Could you write this? Okay, please take 15 seconds to write this down. Yeah?
For the answer, will there be a comma in between?
No, like that, just 1, 3. Now you need a comma if you have a 10, for example.
Right, it's just like a 13 and some.
Yeah, I mean in bracket it's going to be clear. Okay. Did you write this function like? Yeah, 15 seconds are done. F. So where do I start? 1. 1, where does 1 go to? 3. Where does 3 go to? 4. Where does 4 go to? We close the bracket. And then 2, where does it go to? Okay? We all got this? Now, conventionally, if you have a thing with one bracket, like one thing inside the bracket, you drop it. You just write, this is 1 thing. Okay? Very much, or much better, right? Than this notation. Okay, now why is it better than the other notation? Well, there's a reason. Is that I can compose function nicely. Okay? So let's work with n is equal to 3. Okay? Now I have here 1, 2, 3. Okay? Now, what is tau of sigma? Then, tau composed with sigma. What is it? 1, 2, 3. 1, 2, 3. So, sigma of 1, what is it? 3. Right? So, tau of sigma, 1 goes to 3. Okay? Yeah? We agree? Tau of sigma, apply sigma to sigma 1 is 3, and tau of 3 is 3. So 1 goes to 3. Right? Yeah or no? Okay. Tau of sigma 2, so sigma 2 is 1, right? And tau of 1 is 2, so 2 goes to 2. And then 3 will go to 1. Let's check that. 3 to 2 and 2 to 1. Okay? Now it's also a bit annoying to write this every time. Now let's use this notation. Now how do I write sigma in this notation? So tau sigma, what is it equal to? So first, tau is 1 to 2, 2 to 1. Is it okay if I drop the 3? Tau is 1, 2. 3, which is 1, 2. And sigma is, what is sigma? 1, 3, right? Sigma is 1, 3, 2. Right or no? Yes, sir. The first one, tau. Where? Oh. Where? Oh, here you mean? Wait, let's see. Tau, what is, oh, tau is, oh yeah. Tau is 1, 2, and 2 to 1, and 3 is fixed, okay? Tau of sigma, right? Is tau correct or not? Yeah. And is sigma correct? Yeah. So tau of sigma is 1, 2. Tau is 1, 2. Sigma is 1, 3, 2. Okay, just write them together. Are these correct? I believe so. Sigma 1, 3, 2, right? Sends 1 to 3, 3 to 2, and 2 to 1. And tau exchanges 1 and 2 and leaves 3 fixed. Okay. Now, how do I write this in a better way? I want every element appearing at most once, right? Because it's a bijection. So it starts with 1. Under this one, where does 1 go to? 3, right? Yeah? Now look at this one. Start with 3. 3, where does it go to here? Stays fixed, right? What is tau of 3? 3. So 1 goes to 3. 3, where does it go to? 2, right? Now you're at 2. 2, where does it go to here? 1. So 3 goes to 1. Okay? 2, where does it go to? 1. And 1 goes to 2, so 2 goes to 2. Okay? We do one more example. Let's do more examples. Sigma is 1, 2, 3, 4, and tau is 1, 3, 2, 4. What is sigma tau? Yes, sir. Yeah. Could you please raise your voice? Why do I ignore the 2? I ignore the 2? The 3. Okay. So 1 goes to 3, agree? And under this bijection, where does 3 go to? 3 is fixed. Right? This is tau. 1, 2, and 3 is fixed. 3 goes to 3. So 1 goes to 3, which goes to 3. Pardon me? Yeah, exactly. Fixed means it's alone in the bracket. Conventionally, we remove it. Okay? Great. Sigma tau. Let's write this. So I write sigma 1, 2, 3, 4. And then I write tau 1, 3, 2, 4. Let's start with, where should I start? Usually where's better to start? 1. Let's go to 1. Let's start with 1. Under this, where does 1 go to? 1 stays fixed, right? Then 1 goes to 1. Well, then you're at 1. 1, where does it go to? 3. Great. You're at 3. 3, where where does it go to?
4.
4. So 1 goes to 4. Okay? Great. 4, where does it go to? 2. 2, what happens to it here? It's fixed. So 2 goes to 2 here. 2 goes to 3. Great. 3, what happens to 3 here? Fixed. Then 1. And 1 goes to? Okay. Now, if things are coherent and things are correct, 2 should go to 1. Okay? Because it's a bijection. Let's check this. Where does 2 go to? 4. 4, what happens to 4 here? Fixed. And 4 goes to? So 2 goes to 4. Okay? Should I do one more example? Let's do one more.
Can you explain the notation you're using? I'm not sure to understand what you're doing.
What do you mean? Why am I multiplying? What do you mean by notation?
What are you doing?
Oh, so here you're just composing them. This is how you multiply them. Right? What is sigma tau? What is sigma tau of what? Everyone, what is sigma tau of 1? It's sigma of tau of 1. Right? What is sigma tau of 1? Tau of 1 is 2. It's sigma of 2. What is sigma of 2? It's 4. Right? You're just writing sigma tau in a nicer way. Okay? Is it clear? Yes, sir.
And we agreed that there's cyclical symmetry. Like 2, 1, 4, 3 is the same thing.
2, 1, 4.
Into a
Yeah.
cyclical transition.
Yeah. What do you mean? Oh, no. You mean like, I don't understand. What do you
There
mean?
you put 2, 1, 4, 3.
2, where did I put this?
Instead of 1, 4, 3, 2.
1, 4, 3, 2. 2, 1, 4, 3 is the same, yeah.
Okay.
Are we good here?
Just why is tau of 1, 2?
Y is?
Tau of 1, 2.
Tau of 1. Look at tau. The definition of tau. Oh, here. Tau of 1. Oh, tau of 1 is 3. What am I saying? Tau, oh, I'm looking upstairs. No way. Sigma tau of 1. Sigma times tau of 1. So it's sigma of tau of 1 is 3. Sigma 3. And sigma of 3 is 4. Okay? Is this notation clear or not? You should get used to it. This is what we're going to use. Right? This is just a better way of writing sigma tau. Okay? It's confusing. I agree. It's very confusing at the beginning.
The thing is that you jumped into the practice without explaining how it works. So
Pardon me?
it's harder to understand what
Yeah.
you mean by all those things you're doing. And you
I mean,
didn't
you know.
explain what you're trying to do.
I'm just writing it in a better way. Right?
That's not what I
Let's redo an example. Hey guys, let's redo an example. What is the cycle? What does it say? I just want to write it in a better way. I just want to find an efficient way of multiplying them. Okay? Now, let's look at sigma. Sigma 1, 2, 3, 4, and this is 1, 2, 3, 4. What does sigma do? Well, let's start with tau. I'm gonna start with tau. Tau here. Okay. What does tau do? Tau of 1, what is it? Tau of 1 goes to 3, and 3 to 1, 2 to 4, and 4 to 2. Great. Now sigma of 1, what is sigma of 1? 1 to 4. Sigma, what is sigma? 1 to 2, sorry. Sigma 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Now what is tau sigma? Tau is tau composed with sigma. 1, 2, 3, 4. 1, 2, 3, 4. Okay? What is tau composed with sigma? Where does 1 go to? 1 goes to 3 and 3 goes to 4, so 1 goes to 4. Agreed? 2 goes to 4 and 4 goes to 1, so 2 goes to 1. 3 goes to 1 and 1 goes to 2, so 3 goes to 2 and 4 goes to 3. Agree with this? This is the regular composition. Now how do you write this in a nicer way? Where do you start? Where do you want to start? 1. Where does 1 go to? 4. Where does 4 go to? Where does 3 go to? When you multiply them, what is better? This one or this one? What is faster?
I think like that one, because you can visualize it.
This one you can visualize, correct? But you agree that the two are the same.
I mean, they are the same, it's just like, you know, you're kind of used to this one.
You're used to this one, but if I give you like 10 multiplications,
Oh, it's not.
exactly, we're not going to stick to one. We're going to do 10, 12 sometimes. Yes?
So is it like decomposing functions into smaller like segments?
Exactly, yeah.
Is there a name to like functions that cannot be decomposed?
No, I mean all functions on finite sets can do. Okay? Yes? In this case maybe. Okay? Normally it's not true. Okay? It's just a coincidence, yeah. By coincidence it doesn't always it's not always true. Okay, should we do one more example? Let's do one more calculation. But is it clear why I use this notation? Okay? It just makes it easier. I multiply them this way. It's better than multiplying them this way. It's better than multiplying them this way. Yes, sir. Guys, please. Is there a?
Some sort of method to obtain the product of the two lines, or you just kind of have to walk through the
You have to walk.
So if there was 12 compositions, you have to walk.
Yeah. Right. I mean, we'll see. We might see later. Better ways of doing it, but in general, that's it. Yes.
The second bottom line there, is there supposed to be a circle?
Where? Here?
Sigma tau, yeah. No, I'm just wondering if it's
Yeah.
straight up here.
There should be a circle, but I'll be dropping circle.
Okay.
Okay.
Just wanted to make sure.
Yes.
So on the right hand side here, where you've drawn the things in, you've drawn from like tau through sigma, but at the end.
Oh, what am I saying? It's sigma tau. Oh gosh. Thank you. Sigma tau. Thank you. Okay, is it clear? Should we do one? Let's do one more example. Okay, it's so let's write 1, 2, 3. Tau, okay. Yes, sir.
Can you do that with size bigger than 4?
Yeah, sure. You could add one. Okay. What is sigma tau? I mean, if you want, you can. Sigma tau. First, sigma tau, let's write what sigma is. 1, 2, 3, 4, 5. And 1, 4, 2, 3. Okay? For now, this is the best way we have. Later, we'll see better ways of doing this. Okay, more efficient. Okay. What is sigma tau? What do you want to start with? 1. 1 under 2, 3, what happens to it? Unchanged, right?
4.
1. 4, what happens to 4 here?
5.
5. 5, what happens to 5 here?
7.
Okay, let's try this. What is sigma of tau of 1? This is sigma of tau of 1. What is tau of 1? Tau of 1 is 4. It's sigma of 4. What is sigma of 4? It's 5. Okay, so sigma tau of 1 is 5. Clear? 1 goes to 5. Now you're at 5. 5, where does 5 go to? 5 here is?
Not to itself. Not to itself. Not to itself.
3. Right? Are we good here? So sigma tau of 5 is sigma tau of 5. Tau of 5, what is that? Tau of 5 is 5, so it's sigma of 5. And sigma of 5 is 3. Right? I'm always making sure that I have the right answer. Okay, now where does 3 go to? 3 goes to 2. 2 stays fixed here, right? Then 2 stays fixed here, then goes to 1. Then 3 goes to 1. Okay? Great, what do I have left? I have 2 numbers left. I have 2 and 4. Let's start with 2 and see what happens to 2. 2 goes to 3, 3 stays fixed. 3 goes to 4, and 4 stays fixed. So 2 goes to 4. Okay? And that's it. I close the bracket. But before, let me check. 4, what happens to 4 here?
Goes to itself.
Goes to itself. So 4, 4. 4 goes to
1.
1. 1
Goes to itself.
and 1 goes to. Is it clear now? Is it more clear? It's just a notation, and it's a better notation. Okay, we'll see later why. I just want you to get used to the notation. I will post some practice problems on this, just like giving you functions like that, and write them this way. Okay? And you know, in 1 week, you will find this very easy. Okay? Maybe. Okay, great. Great. Now, this notation is very important. Please get used to it. I mean, what time is it? 11. Okay, do you want me to do more examples on this? Should I do? Okay, let's do another example on that. Sigma. Well, okay, let's find sigma tau. Let's write this 1, 2, 3, 4, 5, 6. And what is tau? 1, 2, 3, 4, 5, 6. Great. What do you want to start with? 1. Where does 1 go to? 1. Fixed, right? Fixed goes to 2. 2 goes to 3. So 1 goes to 3. Right? Great. Where are you at now? 3. 3, what happens here? Everybody? 3, what happens? Everybody? 3, what happens here? Fixed. 4. Fixed. 3 goes to 5. Okay? 3 is fixed. So 3 goes to 3. 3 goes to 4. 4 is fixed. 4 goes to 4, and 4 goes to 5. So 3 goes to 5. Okay? Great. 5. Where does 5 go to? 6. What happens to 6 here? So 5 goes to? What do I do here? I close the bracket. Very good. Now what do I have left? Where do you want to start? Choose. Let's see 2. 2. So 2 is? Right? Now it's much more clear, I guess. Now what do I have left? 4 and 6. Let's see. 4 is then 3, then okay? Are we good?
Yes.
Is it clear? Now what happens to 6? It's fixed, right? Obviously, because it's a bijection from 1, 2, 3, 4, 5, 6 to itself. So all of these, so 6 is fixed. Let's double check that. 6 goes to 5. 5 is? Okay, so 6 goes to 6. Okay, it's just a, you'll get used to it. Okay? Pardon me? Okay, yes sir. Why did I? Is that what you mean? Could you, guys, please, yes? Could you? I close the brackets from here. 2, okay, so 2 is fixed here, right? 2 goes to 2. To 2. 2 goes to 1 here, right? And 1 goes to 2. So 2 will go to 2. So 2 is fixed. Okay? In the bracket before? Okay, so let's look at here. 1, 3, 5 is clear. Okay, now you're at 5. Where does 5 go to? 6. Where does 6 go to? 6. 6. And then? So 5 goes to 1. Okay? Now, you write 1, 3, 5, and then you write 1, 3, 5, 1, 3, 5, right? It just, the cycle will repeat itself. So you just close the bracket. Okay? Then, you've seen how sigma tau behaves on 1, 3, and 5, right? Then you have to see what happens on 2. 2 is fixed, so you close the bracket. 4 is fixed, so you close the bracket. 6 is fixed, so you close the bracket. Clear? Yeah, thank you. Yeah?
Is it associative?
Yes? Yeah. Very good question. This is associative, yeah. This is the same way as composing functions, right? If composition is associative, then this is associative. Okay? Should we do one more example? Should we do one more, or this good? It's good? It's good? Let's do one more. And sigma. Well, let's use S9, say 1, 2, 5, 6. Okay, let's use this. Okay, what is tau sigma? So you write them down, and you know you don't need to. Okay, let's start. Where do you want to start? 1. Okay, 1. 1 goes to 1. So 1 goes to 1, 3. Great. 3 goes to 5 goes to 6. Oh, a sigma, right? 5, 6. Then 6 stays fixed. 6, and then 7. Oh, okay, you meant 7 at the end. You meant the final 7.
Yeah.
Yeah, okay, very good. Yeah. 7. What happens to 7? Goes to? So you close it. Great. What numbers do you have left? 2. 2 goes to, and 1 goes to, so 2 is fixed. 3 goes to, and 4 goes to. 3 goes to 4. Oh no, 3 is there, right? 1, 2, 3. 4 goes to. 4 goes to 3, and 3 goes to. 4 is fixed. 1, 2, 3, 4, 5, and 6 goes to 5, and 5 goes to. Yes?
Is it a coincidence that in your last two examples, the odd numbers are grouped together and the evens are separate?
Pardon me?
Is it a coincidence that in the last examples, you have the odd
Oh,
numbers
yeah. Yeah, I mean, you know, the idea is that, yeah, the second one will make things look nicer, right? Because I'm taking the sigma to be consecutive numbers, and the tau, the consecutive numbers, but paired in two, okay? Every calculation is a coincidence. Well, a lot of calculations are coincidence, okay? That way I can expect what the answer is. So it's for me to check that I did not mess it up, okay? Yes?
Every time you have something like a single
Signal is single number in a bracket.
separate amount. So,
Very good. Okay, are we good here? Is it clear? Is it clear how to multiply, how to compose by notation in the sigma and in this notation?
It's a weird thing to do.
It's a weird thing to do, but it makes things way easier. Right? Imagine you have to compose like 25 functions. How would you write sigma tau, how would you like compose them? It's easier to write them this way. Right? If you have like sigma 1, sigma 2, sigma 3. Okay? Then you have 1, 2, 3, 1, 2, 3, 1, 2, 3. And I tell you compose sigma 3, sigma 2, and sigma 1. It's gonna be a bit difficult to write down everything. It's not gonna be very difficult, but it will still take more time. Now we'll see why this is useful later on. This has a lot of applications. Once you see 1, 3, 5, 7, for example, you can tell me everything about the bijection. Once you see 1, 3, 5, 7, you can tell me what's the inverse. For example, one, 3, 5, 7, consider tau to be 1, 3, 5, 7. Okay? What is tau inverse? Yes, sir. So, sorry, yeah. So, I want to start by tau inverse. Just before tau inverse, so you have sig tau is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Tau 1, 2, 3, 1, 3, 5, 7. 1, 3, 3 to 5, 5 to 7, and 7 to 1. Okay, and everything else is fixed. Oops. Okay, what is tau inverse? How do you find the inverse? Yes?
You reverse the parentheses.
I reverse the parentheses. What do you mean by reverse the parentheses?
Everything inside the parentheses just goes the other way, so just
So let's
switching
try.
each
So 7, 5, 3, 5. Is that what you mean?
No, 7, 5, 3, 1. You're
7,
reading
5.
the opposite
This.
way.
What is this? This is
You're reading the opposite direction.
exactly. So what is it? What do you want me to write down?
7, 5, 3, 1.
Okay. Under the inverse, tau inverse. What is tau inverse of 1? Tau inverse of 1 is 7. What is tau inverse of 3?
It's 1.
Okay. You see that? It's much easier. Tau inverse of 5 is tau inverse of 3 is 1. Okay? 7, 5, 3. Are we good here? Is it clear why? Is it clear why this notation is better? Yes, sir.
For the notation of tau inverse, you can't say equals tau, right? I mean, what do we write?
Tau times tau inverse. What do you write this? This is just 1. Identity. Okay? Sure. This? Sure. Okay? Are we clear here? Is it clear? Is it clear why this is useful? You can find the inverse immediately. You can do many other things immediately. So let's look at, well, I mean, that's for later, but is it clear here? Is it clear if I give you a series of bijections in this cycle notation? We call this a cycle notation. Is it clear why how we multiply them? And it's a very, very quick way. Then we're going to see later we're going to see other or some useful tips to help us multiply these cycles. Okay, great. Now, what time is it? 21. Okay, so I've got a lot of questions on question 6 on the assignment. Okay, so maybe I will try to clear that right now. The question states, we have the set of 2 by 2 matrices. A is a 2 by 2 matrix. So define a relation with a set of 2 by 2 matrices. Say that they are related if and only if there exists an invertible 2 by 2 matrix P such that A is P, B, P inverse. Okay? Now you prove that this is an equivalence relation, and I ask you to show something. That a matrix A, B, C, D belongs to the equivalence class of D, where D is, I had 4, 1, minus 2, and 1. Is that what I had? Yeah. And A plus D is equal to 5, AD minus BC is equal to 6. Now this is not supposed to be any lengthy calculation. Okay? You're supposed, I think the way I thought of it is that you're supposed to do it not one way, I mean you can do it 1 implies 2 and 2 implies 1, but you could immediately hit the equivalence. Okay? Now, in linear algebra, what does this remind you of? A is equal P, B, P inverse. Does it remind you of diagonalization?
Yes.
When you look at diagonalization, A is P, B, P inverse. If A is diagonalizable, you can find a B if B is diagonal, and B will be the matrix of eigenvectors, right? If A is diagonalizable, then B would be a diagonal matrix, for example, and P would be the matrix of eigenvectors. Agree or not? Remember this from 133? Okay. Now, how do you find, how to check that the matrix is diagonalizable? What's the first thing to do? What do you compute? You compute the eigenvalues. Now, to find the eigenvalues, what do you do? The characteristic polynomial. Agree or not? Now, let's look at this matrix D. Is it diagonalizable or not? That lambda I 2 by 2 minus D. So what is that? I'll leave you the calculation to do, and you get it's lambda minus 2 times lambda minus 2. Okay, we all know how to find the characteristic polynomial. 133. You didn't see that in 133? Yes, sir. Okay. Yeah. So 133 is a prerequisite for this course. So I mean, how do you find the characteristic polynomial? This is just lambda 0, 0. Guys, please. Minus, what is D? 4, 2, negative 2, 1, and 1. It's this determinant. Now when you compute this determinant, you factor it, and you solve for the roots. These are the eigenvalues. Okay? Now this means that D is that you have D is a 2 by 2 matrix with two distinct eigenvalues. So D is diagonalizable. So D is diagonalizable, and there exists, let's say Q, an invertible matrix Q such that D is Q 2, 3, 0, Q inverse. Okay? Agree or not? Now, this means that the matrix 2, 3, 0, 0 belongs to the equivalence class of D. Agree or not? You can write D is related to that matrix. Because D can be written as Q, an invertible matrix, times 2, 3, the diagonal 2, 3, times Q inverse. So 2, 3 is in the equivalence class of D. This means that the equivalence class of 2, 3 is equal to the equivalence class of D. Okay? Now, ABCD belongs to the equivalence class of D if and only if ABCD belongs to the equivalence class of 2, 3, 0, 0. If and only if ABCD is diagonalizable. Now it's a 2 by 2 matrix. It's diagonalizable with 2 and 3 as eigenvalues. Is diagonalizable with two distinct eigenvalues 2 and 3. Now it's a 2 by 2 matrix with two distinct eigenvalues. This happens if and only if the characteristic polynomial is lambda minus 2 times lambda minus 2. Okay? And then you solve for it. Well, I mean, you know, I guess I've done it, you know, like when you solve for it, it's going to be easy. Okay? Great.